to have molecular gas to trigger the star formation in the molecular clouds. And this is the conclusion by McLeod, that the formation of molecular gas is controlled by star formation, or in general, by the gravitational collapse. This is the same for the star formation itself. So what we decide to investigate, if we need this dependence on the molecular gas to form stars in simulations, or if we can reproduce the correlation even with more general models for star formation, not dependent on molecular gas. In particular, there are theoretical studies of turbulent magnetized cloud that show that the gas in turbulent clouds follows a log normal PDF, which is showed here, where the main parameters describing this log normal PDF are this logarithmic density with an average logarithmic density which depends on the width of the log normal PDF, and the width which depends on two parameters, the Mach number, which tells us what is the turbulent state of the gas, and this B factor, which tells us the amount of solenoidal versus compressive modes inside the cloud. In particular, it has been shown that compressive mode help into boosting the star formation in clouds, while solenoidal mode have the opposite effect. So the main assumption in these studies is that we can form stars only in the high density tail of the cloud, where the gas becomes Jeans unstable, but not all over the cloud. So if we take this assumption and we integrate we compute the star formation rate inside the cloud, we can find an effective efficiency for the star formation, which depends on the width of the cloud, of the log normal PDF, on the critical density for star formation, which depends on the shock conditions inside the cloud, driven by magnetic fields and gravity, and we can measure exactly this efficiency, which can be self-consistently computed in the simulation without tuning the parameter by hand in order to reproduce the Koenig-Schmidt relation. And in particular, this is a plot of the behavior of this equation, which depends on the Mach number and on the real parameter. And you can see that for low Mach number, almost not the gas, in this case, the cloud is not turbulent, not very much turbulent. And for a high real parameter, which means that the cloud is unbound, the star formation efficiency is very low. So we can only have a few cores which can collapse. But if we go to very bound clouds and very high Mach number, for example, we can get an effective efficiency which can be higher than 100%, where the normalization of this value is the mean density of the cloud and the free fall time at the mean density. So this tells us that if the cloud is very turbulent and very bound, the turbulence inside the cloud can trigger the formation of very dense cores, and all of the gas between the core in the cloud, which is low density, cannot collapse, but this dense core can form stars very efficiently and in a very short time. So what we did in our code is to implement this prescription where we can get rid of all the fudge factor and threshold parameters usually employed in simulations. And this is self-consistently modeled using this small scale, high accuracy simulation. But in order to follow molecular gas, we also had to include the non-equilibrium chemistry of the gas. In particular, in our code, we employed the chemistry library Chrome, developed by Grassi in 2014, and we follow 9 species, so the primordial species and molecular hydrogen with all the states. In particular, we included heating processes and cooling processes involving all these species with photoheating, UV pumping, atomic, all the cooling processes, also H2 cooling. And in addition, we include these 3 processes which have only a tiny effect on the amount of molecular gas we can find in the simulation, but they've been included only for completeness, in order to have a complete network for molecular gas. And for metal cooling, since the number of species, metal species can be very large, we use lookup tables, otherwise the code couldn't run because the network becomes too complex to evolve. And the tables have been computed by using Cloudy by Shen as a function of density, metallicity, and redshift, including the Artin-Madao UV background. Now, if we look at the details of the H2 chemistry we follow, we assume that H2 forms via 2 main processes, the H- associative detachment and on dust grains. In particular, we tested this model onto redshift 3 almost solar metallicity galaxies. So in our case, H2 forms mainly on dust grain because the abundance of dust is quite high, while the H- associative detachment is only important at very low metallicity, so for example for POP3 star formation. And we use a simple prescription by Ura, which scales with the metallicity to compute the formation rate of molecular gas, and this depends on the density of atomic hydrogen and the total density of hydrogen nuclei. And to dissociate molecular gas, we assume we can include the excitation to the vibrational continuum of an excited electronic state and the Solomon process, which is very important when you have radiation. And in order to follow the Solomon process, we employ different beams, radiation beams, to follow all these ionization and dissociation processes and to follow all the non-equilibrium state of our gas. But we know that if we want to model galaxies, we have to include cooling, star formation, but also supernova feedback. In order to model supernova feedback, we assume that all the star particles we can form in our simulation represent an entire population of stars because we cannot reach the resolution to follow single stars in the simulation. It's too expensive and unfeasible today. So we assume that the star particle follows a Chabrier initial mass function, where this is the part of the log normal distribution at low masses, below 1 solar mass. And this is the power law at higher masses. And in particular, this interval is where most of the feedback processes occur. So type 2, type 1a supernovae, and also mass losses, so winds from low metallicity stars. We assume that the metal enrichment is driven by type 2 and type 1a supernovae, and we follow iron and oxygen abundances. And we assume that the low mass star winds don't produce new metals, but only release onto the interstellar medium their initial metallicity. The mass resolution? The mass resolution in the simulation I've run is 1.5 10 to the 3 solar masses. Yes. But I'll show you the details about the simulation in the next slide. And of course, in simulations, since we cannot resolve the very small scales where supernovae are energy conserving, we have to solve the problem of the overcooling. So when we release energy, since we usually dump energy into the thermal component, if we can resolve the energy conserving phase and we can resolve the cooling radius of the supernova bubble, we lose this amount of energy, and the effect of supernovae is suppressed. And so we cannot suppress star formation efficiently. In order to solve this problem, we included a delayed cooling prescription following Stinson 2006 for type 2 supernovae. So this is the numerical setup we included. So we have Chrome for the chemistry. Gizmo is the numerical code we use. Gizmo is a new Lagrangian code, which inherits most of the the basic scheme from SPH, but at the same time, differently from SPH, it doesn't solve the Lagrangian form of Euler equation, but it assumes that the volume is discretized with unstructured cells, similar in the idea of, to the idea of mesh-based codes, and then the Riemann problem is solved across the phases. So we can get the advantages of both the intrinsic adaptivity of Lagrangian codes like SPH, but also we can better treat shocks, which is a typical feature of Eulerian code. So we coupled them together to get Gizmo Chrome. We included the physically motivated star formation prescription, as I described before, supernova feedback, mass losses, and we evolved an isolated galaxy for 400 megayears with these parameters. So it's a galaxy with typical properties of redshift 3 galaxies, with a halo of 2 10 to the 11, and stellar mass of 10 to the 9, and gas mass with 2.4 10 to the 9, and this central bulge, with slightly less than 10 to the 9 solar masses. And we followed it with 1.5 million particles, so that we could reach a resolution of 1,500 solar masses per particle. And the maximum resolution in our simulation, spatial resolution, is 1 parsec. So we can get to the typical scales of molecular clouds in our simulation. So this is only a test to show the behavior of our model. We can see here the density temperature diagram, the abundance of molecular gas as a function of the hydrogen nuclei density and the abundance of atomic hydrogen. And we can see here that there is a sharp transition between the atomic or ionized hydrogen regime around 100 particles centimeter cube. Above 100 particles centimeter cube, most of the gas becomes fully molecular. And this is consistent with what we expect, for example, in molecular clouds. Above 100 particles centimeter cube, most of the gas is in the molecular phase, and is also consistent with previous studies following molecular gas in galaxy scale simulation. And you can see here the density temperature diagram. We can see that most of the gas is cold here because of the shielding. So even if we have an extragalactic UV background inside the galaxy, the gas is shielded and shields itself from the UV background. And so it can cool down efficiently because of the metal cooling down to 100 or lower, less than 100 Kelvin. In particular, at very high density, the gas reaches 30 Kelvin, which is close to the typical temperature of molecular clouds. And you can see this tail here of gas, and this is the result of the delayed cooling prescription, which is an empirical prescription to solve the overcooling problem, but that exhibits this feature where the gas, which should be cold at 1 particle centimeter cube, remains hot because we shut off the cooling when supernova feedback occurs. And you can see here, for example, this tail around 1 particle centimeter cube, which reflects this behavior. So the gas here is which is not as a low atomic hydrogen fraction, corresponds to this gas which is heated up by supernovae. But if we look at the Kennigan-Schmidt relation in particular, we show the contours here which correspond to the Beagle 2010 data. The green one is Beagle 2008, and the red one are from the outskirts of nearby galaxies from 2010. And the green contours are Beagle 2008 here, and Skruba 2011 here. And you can see the contours of our simulation. For the Kennigan-Schmidt in the total gas, there is a very good agreement with the observational data, while for the molecular gas, with this model, you can see that the slope is not consistent with the observations, and also the normalization is quite off. And this is because we are not including in this basic test the local radiation from star, which is an important ingredient inside the galaxy. So in order to solve this, we added two new ingredients in our simulation. So an interstellar radiation field, which is very important, and a clumping factor, because the resolution in our simulation is high, but not high enough to resolve the internal structure of the molecular clouds. And this means that if we cannot reach very high densities, above 10 to the 4, 10 to the 5 particles centimeter cube, we can underestimate the abundance of molecular gas inside the clouds. So for the interstellar radiation field, we developed 2 subgrid models, and we compared them with on-the-fly radiative transfer calculation. In particular, this is the first model we tested. In this case, we started from each cell, gas cell in our box, and we computed from the cell properties the maximum radius, R max, where the optical depth exceeds 1. And then, with this R max defined, we could collect all the radiation from the stellar particles inside this sphere. And we could compute the flux from these stars, which is attenuated with an optical depth estimated using the local properties of the star. Because the problem here is that even if, let's assume that the gas has a low density here, so the R max is very large, but we have a wall of dense gas around the star. So if we don't attenuate the radiation from the star, accounting for these local properties around the star, we overestimate the radiation coming from the star and reaching the gas cell. And in order to attenuate this gas, we assume an effective length, which is a Sobolev-like length, which is the gas density over the gradient of the gas density. In the second model, instead, we exploit the tree structure used for the gravitational force computation. So instead of limiting the collection of stars to a sphere around the gas cell, we use the tree. We collect together many stars when they are far away from the target cell, and then we sum all the flux coming from the different stellar sources in the box. In this case, we can get very efficient calculation, and we can take into account all the stellar sources in the box without limiting to a fixed radius. In this case, since we are collecting computing the flux also from very far away stars, we also had to attenuate the radiation around the gas cells using the optical depth around the cell. And for this case, since for the gas cells, a better representation of the typical scale length of the physical process at the Jeans length, we have the sound speed information because this is gas. We use the Jeans length around the star, and we use the Sobolev-like length around the, around the cell, the Jeans length, and around the star, the Sobolev length, like in the previous model. And finally, we also have on-the-fly radiative transfer calculation, which is implemented using a momentum method with M1 closure, like in Rosdahl 2013 for Ramses. So for every stellar source in our simulation, we compute the luminosity and the flux, the radiation flux, which is injected from the star into the gas, and then we advect all the radiation, accounting for the absorption and processes of the gas in all the cells of the simulation. So this is the fiducial model to compare our subgate models with. And finally, I was saying before that we used a clumping factor. Usually people in the numerical community employ the constant factor, which was tuned to reproduce the correlation, the molecular kinetic relation. But in this case, since with the star formation model is based on the turbulent cloud, we decided to use this to consider this, assume the same structure of the gas on our unresolved scales, so a log-normal PDF, and self-consistently compute the clumping factor for the molecular gas. So in particular, we know that this is the formation rate equation for the molecular gas, but this is based on the average densities we can measure in our simulation. Since we can, the density is not representative of the real density in the gas, of the gas in the galaxy because of the resolution limit, if we assume that it's the average we measure over the resolved scales, we can re-express this relation using the average densities and naturally an additional factor, which is the average of rho squared over rho squared, rho average squared, which is the clumping factor. And if you assume a log-normal PDF, the clumping factor is automatically defined with this expression. So it depends only on the Mach number and on this B factor. So these are the results, just a qualitative view of the galaxy with the three models. This is the first model I described. This is the second one with the gravity tree. And this is the RT simulation. And you can see that they are quite similar, except that in this one, the gas distribution is slightly smoother. And then I'll show you later a more quantitative view. While in this case, the spiral arms are better defined. For the thickness of the disk, there is almost no difference among the different simulations. If we look at the molecular gas instead, we can see a clear difference now. So in this case, the molecular gas is more abundant in the very high density regions, while in this case, there is a smoother distribution with molecular gas forming also at lower densities. While for the thickness of the disk, in this case, is a bit thicker, but it's a very tiny difference. So from a quantitative point of view, instead, we can see now the abundance of molecular gas as a function of density for the three different runs. And you can see here that there is a tail, a higher, redder color here, which represents a larger abundance of molecular gas at intermediate density, around 1 particle centimeter cube, while in this case and in this case, the amount of molecular gas at this intermediate density is lower, and there is a larger abundance of non-molecular gas, so it's mostly atomic in this case. So there is a clear difference here for the first model, while the difference between these two models is very tiny. And this is also reflected in the second plot, where we show the atomic hydrogen abundance, and you can see that at the same time we have a larger abundance of molecular gas, and we see a tail of low fraction of atomic gas here. Because the gas here is converted into the molecular gas, so the abundance here is higher, and this is lower. While in this case, the agreement is much better. If we compare with observations, and in this case, we integrated over different line of sight, and we compare with the observations of the Milky Way and the Large Magellanic Cloud, you can see the different simulations with the 2D histograms and the data points, which are the observations. In this case, the model overproduces molecular gas, and we can reach very high column densities here, while in this case we cannot reach 100% in none of these two. The only difference between these two runs instead is at very low column densities, because the RT simulation shows a larger abundance of molecular gas here, a larger abundance of gas with this low column density compared to the subgrid model. If we compare the star formation history of the galaxy, we see that the first model has a lower star formation rate, even with the peaks. The star formation is typically, well, the scatter in the evolution is lower compared to the others. The other two cases show very strong peaks with a lower star formation rate in the other phases. And the peaks in this case, for example, the first peak is consistent between the two runs, which is consistent with the fact that they are more similar. Also for the star formation as a function of time, we see that the first model, which slightly overproduces the molecular gas, has a lower star formation rate and has a lower stellar mass at the end of the simulation. While the other two runs, the RT and the second subgrid model case, show a much better agreement. And again, if we compare the Cannicka-Schmidt relation, we see that for the three runs, there is almost no difference in the total gas Cannicka-Schmidt relation, and this is reassuring because it means that the Cannicka-Schmidt relation is very robust, and so we can almost always reproduce this relation in the simulations, while for the molecular Cannicka-Schmidt relation, the differences are much larger. In particular, the first model, which overproduces the molecular gas at lower densities, is on the right compared to the other two cases, and also the slope is a bit off. While the other two runs are very similar, so the RT and the second model, and they agree very well with observations, except for a small overshooting here, which could be due to numerical effects, also to the fact that the supernova feedback model becomes less effective when the densities are very high. So we can conclude with this test that if we don't want to use on-the-fly radiative transfer calculation, which are very expensive in simulations, the second subgrid model with the second subgrid model, we can obtain very similar results to the RT calculation, while the first one is a bit less accurate. After this, we want to understand what was the role of the clumping factor, because we could reproduce the Cannicka-Schmidt relation in the molecular gas with the clumping factor, but we wanted to assess the importance of this additional factor. And so we also ran our one simulation with a fixed without the clumping factor. And you can see here, when we compare the face-on and the joint view of the galaxy, that we form much less molecular gas in the galaxy. And also the molecular disk is thinner in this case than in this case. If we look at the abundance of molecular gas, we also see that in this case, we get to the transition at very high densities, and in this case is a bit shifted toward lower densities. And also the amount of molecular gas we have here is much larger, consistent with the map I showed before. And for the Cannicka-Schmidt, again, in the total gas, there is almost no difference, because of course, if we underestimate the amount of molecular gas, most of the gas remains neutral, because it's cold anyway. So the total, the sum of atomic hydrogen plus molecular hydrogen is the same, and indeed the relation is preserved. But if we look at the Cannicka-Schmidt in the molecular gas, this is our fiducial case for the RT simulation, and without the clumping factor, we move here. And this is not due to the fact that the star formation rate is different, because this relation tells us that there is no difference in the star formation rate, but the amount of molecular gas is very different. So the relation is offset to the left of the plot, of almost 1 order of magnitude. So we underestimate the molecular gas abundance by 1 order of magnitude if we don't include the clumping factor. And finally, we wanted to understand if it's necessary to employ an H2-dependent star formation prescription. So we estimated the star formation efficiency in our simulation from the gas properties, and you can see here how the star formation efficiency increases with the density, where the gas becomes more turbulent and denser, and so the free fall time is shorter. And you can see that the natural threshold in temperature arises from this model, from our star formation prescription, because when the gas is hot or warm, the turbulence, the Mach number is typically lower because this gas is pressure supported, and so it cannot form stars very efficiently. And indeed, we have a very sharp decrease of the star formation efficiency with the increasing temperature, while most of the star formation occurs in the cold and dense gas. Just to compare with the star formation prescription based on the molecular gas, we estimated the epsilon zero factor, taking our star formation rate and dividing it by the abundance of molecular gas. In this case, we plotted the star formation efficiency as a function of the molecular gas abundance, the density, and in this case, instead, is the epsilon zero factor. And you can see here that the epsilon zero factor is not constant. And in most of the paper and the studies employing this prescription, people usually assume that epsilon zero could be a constant fudge factor between 0.1 or 100%. But according to our results, this is not correct. Also, epsilon zero is a function of the abundance of the gas density, and this should be taken into account. So this was, of course, only a validation of the model, and the aim of our study was to go on and to study more in detail as a scientific problem. In particular, we want to study the kinematics and dynamics of high-redshift quasars, and this is what I'm currently working on. So we want to model a very massive halo at redshift 6, which is expected to host a massive black hole with very high resolution. So we want to go down to 5 parsec for the spatial resolution of our simulation, and the mass resolution is only 10 times larger than the resolution we could achieve in our isolated case. So it's a very expensive study. It's currently ongoing. I will show you in the next slide the preliminary results for a low resolution test I performed. And then we want to include, expand our network, include carbon, oxygen, and silicon to study the formation of C+ in dwarf galaxies using the network we already tested in a paper now in press by Capello et al. So just to conclude, this is a low resolution test without the chemistry to validate all the other prescription in our cosmological simulations. So star formation, a new model for supernova feedback. And these are the properties of the galaxy host as a function of redshift. So you can see here the star formation rate, which rises very quickly to around few hundred solar masses per year, consistent with recent observations by De Carli et al. Of massive galaxies at redshift 6. And this is the stellar mass we could find in our simulation. The different lines correspond to the star formation rate and the stellar mass estimated using the stellar particles in our simulation and using the UV luminosity of our stellar particles. And you can see that when the mass is low, there is a very large difference. So if we use the real mass measured in the simulation, the stellar mass is much higher than the one using the UV luminosity. And this is consistent with the fact that when the galaxy is small, supernova feedback is more effective into sweeping away the gas, and so the star formation is bursty. So depending on when we measure the star formation rate and the stellar mass, usually from the UV luminosity, we underestimate the real stellar mass because we have only discrete events of star formation, and we have a long time between these events. So the UV luminosity has time to decrease, and the measure we can obtain is lower than the real stellar mass we have in the galaxy. For the star formation rate, the difference is a bit lower, but it's still consistent. For the black hole mass, we started seeding a black hole with 10 to the 6 to avoid spurious scattering due to the gravitational interaction. And you can see that the black hole almost grows at Eddington for most of the time, and it can go up. This has been run only down to redshift 7. It will go up above 10 to the 8 solar masses. And we could also measure a black hole merger between two of the most massive black holes in the simulation around redshift 8. Sorry? Why the black hole mass is? No, it's not increasing. This is high redshift, this is low redshift. Well, because there is accretion and feedback. Yes. The black hole is usually in the center of the galaxy, is a massive black hole, so there are large inflows, especially because this is a massive galaxy at high redshift, so the critical density of the universe is much higher, the galaxies are much smaller, so if we have strong inflows, the black hole can accrete a lot. And it almost accreted Eddington because the density is so high close to the black hole that even the feedback is not powerful enough. So you can heat up the gas, but then cooling is very strong, and so the gas goes down again and falls toward the black hole, and it's accreted again, and the accretion is and this is consistent all with other studies by Feng and Di Matteo from the blue tide simulation, for example, where they show that these massive black holes are usually hosted in massive galaxies, not the most massive one, but massive galaxies at high redshift with strong inflows toward the center, and when they accrete, there is no hope to stop them. They accrete almost at Eddington for most of the time. But anyway, this is down to redshift 6, which corresponds to 1 gigayear. So it's only the first gigayear of the universe, and it's only for the most massive object we have. In this plot on the right, just to conclude, we show this, the stellar mass versus the star formation rate. So it's the main sequence at down to redshift 6. So these are the different data points of our galaxy as a function of redshift, and the lines here correspond to the models by Salmon 2015. Sorry, it was the archive version from 2014, but it was accepted in 2015 at redshift 6 with the solid line, red line, and extrapolated to redshift 9 with the dashed line. And this is the Beruzzi model at redshift 6. So you can see that our galaxy moves toward the observed relation. This is down to redshift 7, so we still have a few hundred megayears to run, but the galaxy is moving toward between the two models by Salmon and Beruzzi. So this is consistent with the constraint we have at high redshift. So this seems promising for the high resolution run, which is now ongoing with all the chemistry and model, and the aim is to study the molecular gas properties in these high redshift quasars. So these are the conclusion of the study. So we found that the correlation between molecular gas star formation rate can be naturally reproduced if we account for all the most important processes and for a self-consistently defined but still a clumping factor. And the correlation is maintained also at low molecular gas densities, which are not yet accessible by observations, but we hope in the future to have more data and to compare the model with this new data. And more important, the H2-dependent star formation prescription is not necessary in this simulation. So if we consider a physically motivated model and we have high enough resolution, we can reproduce this relation without assuming by hand that the star formation depends on the molecular gas. And we tested it at low resolution, around 10 to the 4 to the 5 solar masses per particles, and the model is still valid. And this is reassuring because in the cosmological resolution, we cannot achieve 10 to the 3 solar masses per particle, but only 10 to the 4. So if the model still works, this tells us that probably in the cosmological simulation, the results will be reasonable. So, thanks.
Thanks, Alessandro. Is there any question?
Is there any physical motivation behind the use of an initial supermassive black hole with a million solar masses instead of another one?
Sorry, can you repeat?
If you go back to your
Yes.
Yes. So you start the supermassive black hole with a 10 to the 6 solar masses.
Yes.
So is there any physical motivation for that?
This is a low resolution test, as I should say here, wrote here, that the gas particle has 3 10 to the 6 solar masses. And one of the main problems in these simulations is that when you see the black hole, you want to see it with the lowest masses, lowest mass you can achieve. But the problem is that when you solve the gravitational interaction, if the mass of the black hole is too small compared to the mass of the other particles, you can have slingshots, which kick the black hole away from the galaxy. And this is a spurious effect due to the resolution of the simulation. So what usually people did was to, well, there are two solutions. One is to include an artificial dynamical friction to try to keep the black hole around the center. So when it's kicked away, then this artificial dynamical friction boosts the fallback of the black hole toward the center. And the other approach, which is usually employed in very low resolution simulation, is to replace the black hole and put it back to the center of the galaxy by hand. And you can get which is, well, hidden under the rug, but it's a problem of the simulation. So since we didn't want to include these artificial models, because in the high resolution simulation we will have high enough resolution to not to employ them, not to need them, we decided to test it using a massive seed so that the gravitational interaction couldn't produce these spurious kicks. But it was only a choice motivated by this idea.
Have you checked whether changing that mass affects your results or not?
I tried to increase the mass, so I tried to see the black hole with 10 to the 7 instead of 10 to the 6, and the final mass is almost the same. The difference is that in this case, the black hole starts to grow around redshift 12. In the other case, it was constant almost down to redshift 10 or 11, and then it starts to grow a bit, and then it realigns more or less with the other simulation. Because of course, if you have a higher initial mass seed, you can have gas accretion, but also the feedback, since it's Eddington limited, can be much stronger. And so you can heat up the gas and stop the accretion for a while, and then you get new accretion. So the initial phase, in the initial phase, the black hole couldn't grow, where the initial mass was higher, and then it realigns more or less with this other simulation.
Okay, thank you.
Nice talk. So I had a question. I didn't get it maybe quite well. So at the beginning in your introduction, you said that the star formation in principle does not need molecular gas.
Yes.
Is it correct?
Yes.
So then my question is that what was your motivation to consider or start with the molecular gas in your simulations?
I'm not assuming that the star formation depends on the molecular gas. That's exactly the point. I'm assuming that the star formation efficiency is consistent with the studies of turbulent clouds. So it comes self-consistently from the results of these log-normal PDF turbulent clouds, but there is no dependence on the molecular gas. And I wanted to see if we could reproduce the molecular Koenig-Schmidt relation. But there is no dependence. What I showed here, for example, which can be a bit misleading, is that if we assume that the star formation rate we measure in the simulation can be written in with this equation, so with the dependence on the molecular gas, this is our epsilon 0. But in reality, this epsilon 0 FH2, it's the epsilon I use in the simulation, but without any dependence on the molecular gas. So my epsilon comes from this equation. This one. And you can see here that there is no dependence on molecular gas. This is the width of the log-normal PDF. This is the critical density, which is written here and depends on the Mach number and on the virial parameter, and that's all. This epsilon star is a fudge factor in these models, which takes into account the protostellar feedback when the first stars form in the cloud. And it's a factor of 0.5. And this takes into account the uncertainty in the freefall time, and is another factor is a factor of 2. But when you have this equation, there is no dependence on the molecular gas.
So then you mean that the Koenig-Schmidt relation in terms of the molecular gas is just kind of secondary correlation. It's not.
Yeah, I tried to see if we could reproduce the correlation without assuming it a priori.
Mm-hmm.
And of course, to do that, you have to follow on the fly the non-equilibrium chemistry of molecular gas.
And so the next question is that did you try to see the effect of the Alfvénic Mach number as well?
Sorry?
Alfvénic Mach number, because you included the turbulent Mach number
Mm-hmm.
in your models.
Yes.
So what about the Alfvénic? So because you're not.
No, because I don't have magnetic fields in these simulations.
Okay.
Because it's another order of degree of complexity to be added to the simulation. Of course, it's something we want to do in the future because magnetic fields are important and we know it, but this simulation was already a bit expensive with this model.
Okay.
So.
And the next question is that so you also investigated the effect of the radiation field.
Mm-hmm.
But then what's the role of it? I mean, so at the end, if you want to learn something about it, so does it increase the density of a star formation at the end, or decrease it, or what does it do with the molecular gas density?
Well, the interstellar radiation field is important because it corrects, well, since the radiation field can dissociate molecular gas at intermediate densities, what happens is that you shift a bit the relation, the typical density to higher values where the gas becomes fully molecular. And this helps you in correcting the slope of the correlation and get it close to 1, which is what is observed. And when we include the clumping factor, for example, it helps into shifting it on top of the observational results. So the interstellar radiation field and the clumping factor are the missing ingredients in normal simulations to reproduce this correlation. Because if you don't include the interstellar radiation field, you tend to overproduce the molecular gas at low and intermediate densities, and so you don't reproduce the slope anymore. And if you don't include the clumping factor, since the density achievable in the simulation is not high enough, you underestimate the abundance of molecular gas on the unresolved scales. And so you are offset to correspond with respect to the observational results.
Thank you.
You're welcome.
And going back to the supermassive black hole, almost at the end, and I think you are simulating a single galaxy, but you get something like a merger.
No, wait. This is what I've done, but as I showed here, this is what I'm doing now. So it's a cosmological simulation down to redshift 6. So the validation of the model was done on an isolated galaxy with typical properties of redshift 3, just to test that the model was working and could reproduce the observational constraint we have on the gas structure, on the gas kinematics and dynamics. But what I'm doing now is a cosmological zoom-in simulation, with this high resolution, and to study the formation and evolution of these massive quasars. So I want to employ the model I've developed to study massive quasars. And this is the low resolution test where I see this black hole merger, but in the cosmological simulation, you can see there is a redshift evolution for the galaxy.
Yeah, but it looks that there is a merger going on, because it's, I mean, it looks like the black hole is detached from the rest of the galaxy, because the rest of the galaxy is behaving almost.
No, the fact is that this black hole merger occurs between
feedback or something like that.
No, there is feedback, but it doesn't have a strong impact on the galaxy, because this is of course, usually people think about redshift 0, where the density is much lower. But if you look at this redshift, the average density of the universe is so high and the galaxies are so compact. The virial radius of this massive halo at redshift 6 is around 60 kiloparsec. The virial radius. The galaxy is inside 1 or 2 kiloparsec. It's a very compact region. So the density is so high that feedback is not very efficient. And the two most massive halos in the box merge here, but they have one of them has a very large mass. There is a small increase here, less than a factor of 2, in the stellar mass of the galaxy, while there is an increase of a factor of almost 2 in the black hole mass. But they are so massive that you don't see a strong well, the first one is so massive in stars that you don't see a strong effect when it merges with the other one. But everything is so dense that black hole feedback doesn't play a role, and supernova feedback plays a role only at the beginning. So there are oscillations here because you also have a lot of mergers and a lot of interactions, so a few stars are lost during the merger and they are outside the main region where the galaxy is. But then it grows up, and the stellar feedback and black hole feedback don't play a significant role. But of course, here we are talking about the most massive objects in the universe at this redshift. So they are very high sigma peak. They are not normal galaxies.
Any more questions? So I've got one. Alessandro, how do you estimate M star UV from the simulation? I see that there is a nice plot of M star simulation.
Well, I'm using the stellar SED from Bruce-Wallace-Charlot, which is the same I used to compute the interstellar radiation field in the model I showed on the isolated galaxy. So, of course, in this case, there is no chemistry, but I can compute self-consistently the luminosity. And of course, when I'll do it on the high-resolution run with the chemistry and all, the interstellar radiation field could play a role also in the evolution. But in this case, it's only post-processing.
Okay.
So I took the UV flux from the SED by Bruce Wallace and Charlot, and I computed the UV luminosity of the galaxy. And then, well, the scaling relations are the one by Salim and Song for the stellar mass to UV luminosity relation. And
I think that's it. Thank you very much for being here. Thanks, Alessandro.
thanks.
So Alessandro will stay today and tomorrow, is it, in my office that is just above the cafeteria. So if you want to have a chat with him.